Hi, today it's a great pleasure for me to be here at Iwara, even virtually, but sharing our results, our scientific results. The work I will present here today is entitled The Magnetized Photon Properties and Astrophysical Applications. It was done by me in collaboration with other colleagues from the Department of Theoretical Physics of ICIMAF in Havana, like Hugo Perez Rojas and Aurora Perez Martinez, and also with former and present students of the physical faculty of the University of Havana, and also Gabriela Piccinelli from UNAM Mexico and Jorge Rueda from ICRA-NET. So, the final aim of this talk, which is still in progress, is to calculate the photon time delay in a neutron star magnetosphere. To that end, we first study the transverse propagation of photons in a very simple model of vacuum, of a magnetosphere filled by vacuum, considering radiative corrections in the one loop approximations and also in the region of transparency below the threshold for pair creation. And we will analyze the dependence of the photon time delay with the magnetic field strength as well as with the distance from the star surface, assuming a dipole-like configuration for the magnetic field. And as we will see later, we will obtain that photons of higher energy experience a longer time delay for fixed values of the frequency. This work is based on this reference, so you can consult it for any further details you can find. So let's go to the next transparency. Let's talk a little bit about the model we will use. As we already said, we are interested in a photon time delay process occurring in the vicinity of a pulsar and which are not related to the photon interaction with the interstellar medium. So which are the assumptions we will make to study this problem? The assumptions are the following. First, we will consider the simplified model of the magnetosphere. The magnetosphere, we will assume that is composed by QED vacuum electron-positron pairs, that is filled with a magnetized vacuum. And of course, there are more complex models in which the magnetosphere is filled with neutral or charged electron-positron plasma. And we will later consider some of them in future extensions of our work. We will take into account surface magnetic fields, which varies from 10 to 12 to 10 to 15 Gauss, and we will assume a magnetic dipole-like configuration for the magnetic field to estimate the phase velocity and the time delay of the photon, and also we will simplify our model by not including the rotation of the star in it. So we will start from the photon dispersion equation in a quantum vacuum, quantum magnetized vacuum. In this case, we should modify the usual dispersion equation of the photon, which is the 4 momentum squared equal to 0, by adding the eigenvalues of the photon self-energy. This magnitude takes into account the indirect interaction of the photon with the magnetic field through the virtual electron-positron pairs, and is given by these agent values where I is equal to 1, 2, or 3. And here these agent values depends on the photon frequency, the parallel and perpendicular components of the photon moment, and also on the magnetic field, which is normalized to the Schwinger value, Schwinger critical value, which is of the order of 10 to 13 Gauss. In what follows, we will focus on perpendicular propagation because for parallel propagation, the solution of the modified dispersion equation is just the light cone, that is k squared equal to 0. And we will also focus on the second mode, because for the third mode, in the region of transparency, the deviations from the light cone and the time delay are much smaller than for the second mode one. And at this point, we want to stress that for perpendicular propagation, the first mode, that is with I equal to 3 to 1, is a non-physical one, so we do not consider it. The second mode is the one we will focus on in what follows, and the third one is the one we already mentioned, that will give us less pronounced effects, okay? And these values of the agent function of the photon self-energy were calculated previously by Shabbat in 1975, are given by these expressions, and of course give or lead us to the dispersion equation, which must be solved numerically. But these numerical calculations may be considerably simplified if we use this idea. That is, for large range of frequencies, the solution of the dispersion equation corresponds to relatively small deviation from the light cone. That is, this magnitude is really close to 0, except for values for which the frequency is extremely close to the vacuum threshold for pi creation. In this case, we can write in this case, we can write the photon self-energy agent values as polynomials in chi squared, in the form momentum of the photon squared, and which is given by this expression. And we can truncate this expansion at some finite value of L, and we want to point out that even L equal to 3 works very fine, and write the solution in terms of the so-called hypergeometric functions, because in this case, the dispersion equation reduces to a polynomial equation. And the results will be shown in the next slides. Here is the mentioned solutions of the dispersion equation in terms of A hypergeometric functions, and is depicted in this figure. The solution of the dispersion equation is shown for selected values of the magnetic field strength equal to the critical magnetic field 10 times and 100 times of the critical magnetic field. And the figure shows that when the magnetic field increases, the deviation from the light cone is higher. Besides that, for any value of the magnetic field, a threshold exists, which is here, above which the photons have a high probability to decay in a photon in electron-positron pairs. Sorry. For our purposes, we are only interested in the study of the region of transparency, which is this one, which is the region of momentum space where the photon self-energy and its frequency have real values. We also can calculate the phase velocity once we have solved the dispersion equation, and the photon phase velocity takes the form shown here as a function of a magnetic field and for fixed values of the frequencies. We can see from here that photons of higher energy have lower phase velocity than the lower energy ones, and hence the later suffer a longer time delay. And we can appreciate also that in the limit of low frequency, this one, the phase velocity decreases almost linearly with the external magnetic field. And finally, we can estimate, after calculating the phase velocity, the photon time delay. First of all, we assume a dipole-like configuration for the magnetic field, and then we can see how the phase velocity varies when the distance from the surface of the star is increased. Here, B0 and R0 are respectively the surface magnetic field and the radius of the neutron star. And in the figures here, we show the phase velocity as a function of the distance traveled by the photon for different values of frequency and a fixed value of magnetic field, of surface magnetic field. The upper figure, the upper corresponds to 10 to the magnetic field equal to 10 times the critical Schwinger field, and the lower one to the magnetic field equal to 100 times the magnetic Schwinger critical field. And we can see that, of course, the major deviations from the values of the velocity of the velocity of light c in vacuum is achieved for the region very close to the surface of the star, as was expected. And finally, we can also estimate a magnetic time delay in a magnetic dipole-like configuration. These are the last slide, or with the results that we will show to you, and we can observe from here that the time delay of photon as a function of distance for two fixed values of the surface magnetic field, the same as in the previous slide, the time delay is of order of nanosecond for different values of the frequencies, and in spite of this shortness, the results show that the sole presence of the magnetic field is enough to cause a time delay that grows with the photon frequency. And this is the main result of our work that, as I already said, is still a work in progress, and we have a lot still to do to clarify and to calculate also. So let me summarize. Sorry. Let me summarize by saying that the photon time delay in this work was calculated starting from a very simple model of the magnetic field configurations in the neutron star magnetosphere, that we found that differences between the photon time delay of radiation of the order of 1 MEF is of the order of nanoseconds, and that this difference might be due to the fact that the more energetic photons interact stronger with the virtual electron-positron pairs, being closer to the threshold for pair creation. That is, the effect is greater in the vicinity of, for photons which frequency, is in the vicinity or is very close to the threshold for pair creation. And I want to remark finally that the more energetic photons are delayed with respect to the lower energetic ones. And this is our main, I think, achievement here. So that's all. And finally, let me then thanks everybody for paying attention to this talk, and especially to the organizers of IWARA 2020 for kindly inviting me and my colleagues to share here our results, our experiences, and I am very, very grateful to you all for this. Thank you very much. And also, of course, any feedback, suggestion, criticism is most welcome. So you can contact me or any author of the work to share it. Thank you very much again.